method for incremental scanning for snapshot real-time garbage collection. If we are familiar with snapshot GC, this subtitle explains half of.
Microphone, please.
Yeah, this subtitle explains half of my code. And the title of this session is List and Functional Languages, but garbage collection is not only for list nor for functional languages. Many programming languages has garbage collectors, such as Git, Pro, C++, Java, and C#. Nowadays, even BASIC has garbage collector. It's very difficult to find a programming language that do not have garbage collector. Can you imagine any? I can imagine only Fortran and C. So, okay, so I guess that most of you are familiar with garbage collection, but let me start with some brief explanation of garbage collection. In these programming languages, data objects are allocated dynamically, that is, only when they are required. This is a code for this is a small Java code. We have variables x and y of type node, and when we create a new node, x contains pointer to that object, and then when we create another node, and a new object will be created in T, and y will have a pointer to the new object. And when we change the content of left slot of x, then this slot will point to this object. Okay. In this way, objects are allocated dynamically in T. And far after computation, some objects may become useless, and the memory space is limited. So we need to reclaim unused objects so that they can be used for further computation. And the mechanism for this is called garbage collection. Here, garbage is data object that can never be accessed. That is, those objects that are not reachable from the roots. And what are roots? Roots are locations that the program can access directly, such as global variables, local variables, or registers. In this figure, these are the roots, and there are several objects in the key, and this object cannot be read from the root. So this is garbage. And most popular garbage collection method is --C. And this algorithm suspends the application program for garbage collection, and it first marks all objects that are reachable from the roots. And then in the sleep phase, it sees mark phase, it marks all objects reachable from the roots. And in the sleep phase, it sees the entire key, and it grades all unmarked objects. Okay, so the mark phase marks all objects, and then in the sleep phase, it finds an unmarked object and then after that, the garbage collection within the education program. The algorithm is clearly explained as a three-color algorithm. In this algorithm, each object is given a color, either white, red, or black. As far as all objects are white, and for each root, it makes all objects that are pointed to from the root gray. And in math case, while there remain gray object, it chooses one gray object, say X, and makes it black, and then make gray all white objects pointed to from X, like this. Then during the seed phase, it scans the entire heap, and for each object, if it is white, then regrabbing. And if the object is black, then make it white for the next garbage collection. Okay, the problem of this kind of garbage collection is that it suspends application program for garbage collection. And each garbage collection typically takes some seconds to some minutes. In extreme case, it takes overnight. And so this kind of garbage collection is not suitable for real-time applications. So it's like this. The application is suspended and the garbage collection started. And until garbage collection ends, the application is suspended, and this suspension time is not very small. So we need the so-called incremental garbage collection or real-time garbage collection. And in incremental garbage collection, one chunk of garbage collection process is done at a time. Say, mark n object at a time, or see n object at a time. Okay. Then the suspension time of the application program is very small. And the best timing of executing one chunk is each time a new object is created, because this makes it possible that as many objects you consume, you proceed garbage collection as many times. But there is a big problem with this kind of incremental garbage collection. It is that the application program keeps running even during garbage collection. And application program may change different relations in the heap. And this includes that the garbage collector may fail to mark some objects that are still in use. For example, we have three objects here, and this is black, gray, and white. And suppose the application program resumes execution at this point, then it modifies the structure so that it replaces this pointer to this pointer. And then after that, replace this pointer with some different point of view. And then this object remains white, but it is not reachable from gray object. It is reachable only from a black object. So this object may fail the chance to be mapped. To solve this problem, I propose an algorithm for snapshot garbage collection. It uses right barrier. The right barrier of snapshot garbage collection makes gray the object previously pointed to when the pointer is created by another pointer. So if the application program changes the pointer from this to this, then the right barrier makes this object gray. And this right barrier solves the previous the problem in the previous example. There are two steps, and the right barrier was at this point, and this object becomes gray.
But you only do that if it's already white.
Sorry?
What if the previous object is already, say, black?
It doesn't do anything.
Right.
Okay. All objects with snapshot garbage collection, all objects in use at the beginning of the garbage collection are guaranteed to become black eventually. And to guarantee this, the algorithm makes gray all objects directly pointed to from root at the beginning of a garbage collection. So this makes it possible that no right barrier is necessary for writing to the roots. Okay, so this algorithm is quite efficient even on stock hardware. So it is used in many systems. But I proposed this algorithm more than 10 years ago. There was a problem, not a big problem, but I was worried about the problem for a long time. And the problem is that the algorithm has to make gray all objects directly point to from roots at the beginning of garbage collection. And this may cause a wrong suspension of the application program because local variables are stored in the stack, and the stack size changes dynamically. And so if the stack is very long, then the suspension time may become long. This is some figures for two benchmark programs of various benchmarks, Fibonacci and Boyer. And x-axis indicates the size of the stack in words, and y-axis indicates the suspension time for root scanning at the beginning of garbage collection. And in the case of Fibonacci, the suspension time is less than 60 microseconds. And this is okay, but in the case of Boyer benchmark, the stack becomes very long in some time, and the maximum suspension time is more than 200 microseconds. Japanese journal called Business Linux. And it's about a new robot, humanoid, developed by Fujitsu company. And they say that they chose real-time Linux because they want control in 100 microseconds. But unfortunately, they couldn't because they use USB to control the humanoid. USB connectors. And so their current model is controlled in 1 microsecond. So anyway, they want 100 microseconds for suspension. So the key idea of new algorithm is to scan the stack incrementally, not all at once. But this also has a problem. You have scanned this area already, but not yet this area. And suppose there are 3 pointers from the stack to 3 objects. And if the application program changes the structure of pointers, and then this pointer is replaced by this pointer, and this pointer is replaced by this pointer, then this object still remains white, but it pointed to only from already scanned area. So this may fail to be marked. Yes?
Why would the object be subject to the white barrier that paints the object?
Because snapshot garbage collection does not require right barrier for rewriting stack area. That's why the algorithm is so efficient. Okay, things are very simple if you put right barrier. Okay, so to solve this problem, we make use of sort of function frames. I think you are familiar with this notion. When a function is executed, each frame is stacked on the stack. And when f calls another function g, a new frame of g will be pushed on the stack, and this frame becomes a new current frame. And when g returns, this frame is popped up, and then the previous frame will be the current frame again. If g further invokes another function h, then another frame is pushed on the stack, and so on. And the point is that only variables in the current frame can be accessed. So when f is running, it accesses only variables, only local variables in this frame. It does not access any variables in other frames. Okay. Scanning versus return. Okay. We think that it's good if the current frame contains only the words already scanned. But the problem may arise when the current frame contains unscanned area, because the application program may change the structure like this, and then this object may fail to be marked. Okay, so I propose a new notion of new mechanism called return barrier. Return barrier is placed at the bottom of the stack area that has been scanned. And if the current frame if the function returns and the current frame and the new current frame becomes below the return barrier, some barrier code will be executed. The code scans stack a little bit and then push the return barrier at the bottom of the scanned area. Then after that, the function will return as usual. This guarantees that every word in the current frame has already been scanned. And this mechanism is free. I mean, you do not have any runtime overhead to use return barrier. This is a typical frame structure, say, in C language. There is a return address here. And to put a return barrier at the bottom of this area, you just save the return address somewhere and put address of the barrier code, which scans frames a little bit, and after that jumps to the return address saved here. So if there is no return barrier here, then the function returns as usual. But if there is a return barrier, the function the controller automatically transfers to this barrier code, and then the function returns as usual. So, and it's also free in case of Java. And the frame structure of Java is something strange. The return address is stored in the previous frame, but the implementation is essentially the same as in the case of the C language. We just save the return address somewhere and replace it with some address of barrier code. In the case of Java, the return address is actually indexed to the bytecode. So you introduce a new instruction for the barrier code, and you create the index with the index to this code. And since Java has multiple threads, the best place to save the return address will be the thread structure of each thread. And I have implemented return barrier in code commodities, of course. And this is the result of the implementation. This is the suspension times. K0 is the number of stack words scanned at the time. As K0 increases, the time for suspension will increase, of course. But maximum time of suspension is less than 50 microseconds. And so this, so we are very happy with the result. And this is the suspension time caused by the return barrier. When the function returns beyond the barrier, it suspends the application program. And so this is a measurement of that time suspension time. And okay, the maximum suspension time is less than 45 microseconds. And this is a number of suspension time, number of suspensions. This is the result for the Boyer benchmark, and it causes garbage collection 270 times, and but only 24 times, only 24 times suspension made during execution. So the number of suspension is very small. And we have implemented garbage collection return barrier in a Java runtime called JAD, which is JVM system developed by Omron Corporation in Japan. I don't know whether this company is famous in the United States. That was one of the major companies. And they developed a journey processor, journey system for process control. And they had snapshot real-time garbage collection, but they had the right barrier even for routes. So this is their garbage collection is not very efficient originally. So we implemented a return barrier and removed right barriers for routes. And this is a result of benchmark. I don't have time to explain the benchmark, but in the extreme case, this is a time for original system, and this is a time for the revised version. And in the extreme case, the running time is reduced about 15%. And we have also implemented return barrier on this system called USRIS. This is a multi-thread system developed by Tokyo University to control humanoid robots. And so they badly need real-time garbage collection. They implemented snapshot garbage collection, but stack scanning is done at once. So we have implemented a return barrier for the system. Okay, and now they are rewriting the C code. They wrote their code, type critical code in C, in the C language. So they are now rewriting the C code into this. Yeah, this is humanoid robot. And USRIS has a parallel garbage collector. In their original system, they have new data that execute the application program and another thread for garbage collection. These run independently. And new data access, because two threads access the stack at the same time, we need some kind of mutual exclusion. But when we introduce the return barrier, the new data accesses only those areas in the stack above the return barrier. And the collector accesses only those areas in the stack below the return barrier. So there is no log necessary to access the stack for these two threads. And when either of these want to move the return barrier to the bottom direction, then a log is necessary for mutual exclusion. So mutual exclusion is very cheap when you use return barrier in this system. Thank you. Any questions?
How do you deal with growth? Is that much of a problem?
Good question.
premise of this stat scanning with the barrier is that the current, or in this diagram, an upper frame would never access, or particularly never mutate, a lexical variable of some lower frame.
Good question.
Yeah, but the closure.
I have to track for this. If you have a local functions, then as it said, the current function may access some other function frames which is accessible through a static link. So when you scan the current frame and it has a static link, then you have to scan those frames as well. But the length of static link is not very long, so you may additional 3 or 4 scan. This is totally no problem. Yes.
Although I haven't thought about this very much, but it occurs to me that a labels function may be present on the stack from the same definition of the labels function, the same closure, the same identical closure, may call itself recursively,
Yeah.
and exist in the stack. In that case, would you scan